The law of exponential change. This is an application of our differential equations, and we're just going to be expanding what we did in class today. So the law of exponential change says if y changes at a rate proportional to the amount present, that is if dy dt equals ky, and if y equals y sub 0 when t equals 0, then y equals y sub 0 e to the kt. We also write this as y equals ce to the kt. So hopefully you've recognized that this is just that work that we've already done in class. And when we say y equals y sub 0, we could also write that as y equals c when t equals 0. So that just implies that y, or c, is our initial amount. That's the amount we start with, the amount of money we deposit in the bank, the number of bacteria that we started with our petri dish, the initial population of a settlement, that sort of thing. In this formula, you've seen this is actually the solution, the general solution to this differential equation. K is our constant of proportionality, and it will be a growth constant if K is greater than 0, or a decay constant if K is less than 0. So that will just let us know whether we're getting more population or less population, that sort of thing. So let's just run through the solving of this differential equation real quick, just to prove that that is the solution. So we would have dy dt equals ky. Then we would separate our variables. So we would end up with 1 over y dy equals k dt. And we would integrate both sides. So we end up with the ln of the absolute value of y equals kt plus c. We want to solve for y, so we're going to exponentiate both sides. So we'll end up with y equals e to the kt plus c. And like we talked about in class, e to the kt plus c is the same thing as e to the kt times e to the c. So we would end up with c e to the kt. And that just shows you that this is the solution to the differential equation. So let's do some examples, and we'll go ahead and see how this works. Example 1, compounding interest continuously. If you deposit $800 into an account that pays 6.3% annual interest, compounded continuously, how much money would be in the account 8 years later? When we're talking about compounding interest, here the key words to let you know that we're going to be using this formula is that it's compounding continuously. If it's something that's compounding just monthly or weekly or something like that, you would use a different formula. But to use this formula that has the E in it, that's a continuously compounding formula. So how much money would be in the account 8 years later? Okay, this is not really a calculus problem. This is really just an exponential problem, but I wanted to just give you a feel for the variables to remind you how this works. So we would have y equals c e to the kt. Okay, and c is our initial condition, or our initial amount, and so that would be 800. So y would equal 800 e, and then k is our rate. It's our constant of proportionality, and our rate of growth here is 6.3%. Now we do need to be careful because we want this not in a percent, but actually in a regular decimal. So that would be 0.063 t. And then you would just plug this into your calculator. And when we plug it into our calculator, we need to make this be, our t is actually 8, because it said 8 years later. So this would be times 8. It's not letting me erase the t, so times 8. And when we do that, we would get y equals 1324.2634, but since we're dealing with money, we're going to stop at 2 decimal places. So if you deposit $800, if the account pays 6.3% annual interest compounded continuously, after 8 years you would have $1,324.26. Okay, on to an actual calculus problem. Here we have example 2. Bacteria in a culture increased from 400 to 1600 in 3 hours. Assuming that the rate of increase is directly proportional to the population, find an appropriate equation to model the population, and find the number of bacteria at the end of 6 hours. So we're always looking for key words here, and the key word in this particular problem is that it is directly proportional. So that's the clue that that's one of these problems, one of these exponential growth problems. And you're expected to know that that's what this is implying. The nice thing about it is that you don't necessarily have to go through that process every time of finding the antiderivative or solving the differential equation. You get to go straight to the y equals ce to the kt equation. So for part A, find an appropriate equation to model the population. That means that we need to find a c and a k. So we're going to look first. C equals the initial condition. And so our initial condition in this case is going to be 400. So we're going to let C be 400. We got to find K. There isn't anything here that is telling us easily what K is, and so we are going to have to actually use our equation to solve for K. So we're going to go ahead and start plugging in some values. So y equals 400, because that's C, e to the kt. And then we're going to use some information that we've been given, and that secondary information is that it's 1600 bacteria after 3 hours. So that means that this graph is going to go through the point 3, 1600. So we're going to put 1600 equals 400 e to the k, because we still don't know k, times 3. But now we'll be able to solve for k because we've gotten rid of the rest of our variables. So we're going to start solving. 4 equals e to the 3k. Okay, and now I need to solve for k. It's in the exponent, so we would take the logs of both sides. Since this is base e, we're going to take the ln of both sides. So I'm going to do the ln of 4 equals the ln of e 3 to the 3k. You could go straight to the next step, which would be ln of 4 equals 3k. So you can actually go skip over that step showing your taking the log of both sides, and you could just write that ln 4 equals 3k. All right, so then we're going to solve for k. We'll come up here. So k will equal the ln of 4 divided by 3. And if you plug that into your calculator, then you want to be very careful to make sure you close the parentheses after the 4 before you divide by 3, and you would get 0.4620, and it would keep going. It doesn't stop. It's better, in my opinion, to just leave it as k equals the ln of 4 over 3. That's the exact answer. It's a little bit of a pain to write it out, but you can always keep using your k in the problem from here on out, or assign it even a different variable if you wanted to, and then just use that calculation. But just be very careful when you're entering this into your calculator, because this is the ln of 4 parentheses divided by 3, and it's really easy to forget that parentheses, and then it messes you up. All right, so we need to write our equation. So we haven't quite answered A yet. So y equals 400 e, and k is the ln of 4 divided by 3 t. And that is our answer to part A. So now we want to do part B. And part B is a much simpler question. Now that we have the equation, find the number of bacteria at the end of 6 hours. That just means that t equals 6. All right, so we just plug it in. So y equals 400 e to the ln of 4 over 3 times 6. And when we type that into our calculator, being very careful with that exponent, then we get 6,400 bacteria. Don't forget your units. It might be easier when you're dealing with problems like this to plug that equation into y1 and leave the variable in there, and then you can just evaluate it. If you don't remember how to use your calculator at that point to evaluate it at a particular number, just ask me in class tomorrow and I can show you. All right, let's move on to another example. Here we have a half-life problem. These are pretty common for exponential growth and decay. So we've got radium-226 loses its mass at a rate that is directly proportional to its mass. So there's that key word again, directly proportional. All right, its half-life is 1,590 years. And if we start with a sample that's 100 milligrams, the mass is 100 milligrams, then we want to find the formula for the mass that remains after t years. We want to find the mass after 1,000 years, and when will the mass be reduced to 30 milligrams. All right, so find the formula for the mass that remains after 2 years. T years, not 2. All right, so here's A. So we're going to start with our formula, and we know this is the formula because it told us it was directly proportional. And we know that it starts with a mass of 100. So C is going to be 100. The only other information we have is this half-life. And if you've taken chemistry or some of those sciences, you'll know that half-life is when we have only half of the material left. So what that's telling us is that in 1,590 years, then Y will equal only 50, because we started with 100, and that's half of 100. So 50 equals 100, e to the k, 1,590. All right, and now we just would go ahead and solve. So 1/2 equals e to the 1,590k. Oh, that looks terrible. Try that again. So we're going to take the ln of 1/2 equals 1,590k. So k is the ln of 1/2 to 1,590. Okay? And if you type that into your calculator, then you're going to end up with another one of those non-repeating, non-terminating decimals. So once again, I would leave it here as just k, and that helps you. But it ends up being 0.004359, and it's negative, which should make sense because our amount is actually decaying, and so k would be less than 0, which we talked about on the very first page of notes. All right, so the equation then is y equals 100 e to the ln of 1/2 divided by 1,590 t, and that is the answer to part A. So now we're going to look at part B. B simply says find the mass after 1,000 years. So that's when t equals 1,000. So this is an easy one because we're just going to plug it in. So we'd have y equals 100 e to the ln of 1/2 over 1,590 times 1,000. Sorry, that looks so messy. And it's not necessary for you to rewrite this equation out with the 1,000 in there. When you tell me t is 1,000, then you can go ahead and just plug it into your calculator and solve. That's not a problem. And so when you do that, being very careful with your parentheses, you would get y equals 64.6655 milligrams. And so that's how much is left of the radium-226 after 1,000 years. So we haven't lost quite half of it yet, since its half-life is 1,500 years, but we've lost about, 36 almost milligrams. Okay, so then part C. All right, having one of those moments Let's try this again. Part C, not part 6. Where that came from. When will the mass be reduced to 30 milligrams? So that means that Y now is 30. So you're going to put that 30 here in where Y goes, and then fill in the rest of the equation. This is ln of 1/2 over 1590 times t, because we're trying to find when this happens. So you're going to go ahead and start solving. So we would end up with 3/10 equals e to the ln 1/2 over 1590 t. And now we're going to take the ln of both sides, and this is about to get really gross really fast, but that's okay. So the ln of 3/10 equals the ln of 1/2 over 1590 t. So then t is going to equal the ln of 3/10 divided by the ln of 1/2 over 1590, ooh, and that's going to equal, and I'm going to actually write it over here to the left, so t will equal 2761.7752 years. All right, be super careful with those ln's in your parentheses and all of that. If you're having issues typing that into your calculator, again, just let me know and we'll look at it in class tomorrow and I'll show you some shortcuts. Okay, another example. Example 4. Suppose the amount of oil pumped from a well decreases at a continuous rate of 10% per year. When will the well's output fall to 1/5 of its present level? So we've got oil being pumped, but the amount is decreasing at a continuous rate of 10% per year. So there's that continuous rate is our clue here, as opposed to proportional. Either one keys us into this is what type of problem it is. Oops, let me move that. All right, so y equals CE to the KT. We know that the rate is decreasing at 10%. So 10% would be 0.1, but we got to be careful because it's decreasing, so that would make it be negative. We want to know when the output will fall to 1/5 of its present level. Okay, we don't know the initial amount, so we don't know what 1/5 would be, but that doesn't really matter. What that 1/5 is telling us is that when I take the current amount and divide it by the initial amount, it will be equal to 1/5. So we don't have to worry about even finding C here. We can just go ahead and say that 1/5 will equal e to the negative 0.1 t. Again, because if we were trying to solve, we would just divide both sides by c, and then y over c would be 1/5. Okay. So now we want to solve for t because we want to know when. So 1/5 equals e to the negative 0.1 t. We got to take the ln of both sides to get rid of that e and pull the t down. And then we divide. So t equals the ln of 1/5 over negative 0.1. And when you type that into your calculator, you're going to get 16.0943 years. And just be careful, don't forget that negative sign in there. If you had forgotten the negative for the k, when you took ln of 1/5 divided by a positive 0.1, you would have gotten negative 16 years, and hopefully that would have made you stop for a second and go, whoa, it can't be negative years. And then hopefully you would have gone back and seen that k was a constant of decay. All right, another example. Example 5 is our final example. So we've got a population of fruit flies that are growing in proportion to the number of fruit flies. If there are 100 fruit flies after the second day and 300 flies after the fourth day, how many flies are in the original population? So we want to find C. Okay, how many were in the original population? So that is C. We need to use the information given us to help us do that. So let's organize it. We know when T is 2, Y is 100. We have 100 flies. And when T is 4, then we have 300 fruit flies. We're going to use this information to help us then find K, which will then help us find C. All right, so let's write an equation. Y equals C e to the kt. And we know to use that because it says in proportion to. All right, and we can plug in what we know. So I'm going to use my first point, and I know that there's 100 flies. I don't know what C is. I don't know what K is, but I know that T would be 2. So I'm going to write that as 2K. Okay? And then one of the ways you can go about solving this is you can take this, and I solved it for C. So C would be 100 over e to the 2K. And then I'm going to substitute that into the next equation using the second point. So the second point, we have 300 equals, and for C, I'm going to put what I just found. That's C times E, and in this case it'll be to the 4K because T is 4. And then we can solve it. And one of the things to understand here is that you basically have e to the 4K divided by e to the 2K, okay, because this fraction is being multiplied by e to the 4K. And when we do that, we would just subtract the exponents. So we would have 300 equals 100 e to the 4K minus 2K, which is, of course, just 2K. So 300 equals 100 e to the 2K. And then we would solve it. So e to the 2K equals 3, because that's 300 divided by 100. And then we would have 2K equals the ln of 3. And K is the ln of 3 divided by 2. A little bit long, but we found K that way. Now, there is another way that you can do it. It's basically the same idea. It's just a little bit shorter. And you could just create the system of exponentials. I don't know if you learned this when you were doing your exponential unit in 11th grade, but you can do this. So we're writing both equations. And I actually should have written probably the other one up on top. So I'm going to just rewrite this one down here because it's a little nicer this way. And so when you have a system of equations and you are trying to solve it, then you can just divide. So 300 divided by 100 would be 3, and then C divided by C would be 1, and e to the 4K divided by e to the 2K would be e to the 2K. And so that gets us very quickly, down to here. So either way, if you haven't seen it before, though, then that is something you might not have known. So the reason why we solved for K was so that we could then find C, which the question asked how many flies were in the original population. So I'm going to come over here, and Y equals CE, and we said that K was the ln of 3 over 2 T. And using one of our points, I'm going to choose to use the point 2, 100, but you could use either one. It wouldn't matter. So then Y is 100. We still don't know C. e to the ln of 3 over 2 times 2. So those 2's will be nice and cancel out there. And we'll be left with 100 equals c e to the ln of 3. But according to our exponential and log rules, e to the ln of 3 is just 3, so we'll have 100 divided by 3 equals c. Now this is kind of a weird problem because it says how many flies were in the original population, and so this is implying that we started out with 33.3 flies, which would be like parts of flies, and that's kind of a silly starting number. But if this were to work out in a real problem and it didn't work out to a nice whole number, which life doesn't usually work out as a nice whole number, but you would say 100 over 3 or 33.3, and then you could just say, so we started out with 33 flies, because of course that fraction of a fly wouldn't make any difference here. All right, that's it. So I'll have an assignment posted for you, and you can look at those problems and just ask me any questions you have tomorrow. Thanks.